All right, so how to graph sine and cosine and tangent, believe it or not. Tangent does it is slightly different, but yeah, it's a little weirder. But when I do this, I use a box method of solving this. I build a box, and then I build my wave inside the box. Now, the question always comes down to in the very beginning, are you able to draw your graph on your own paper? Or did somebody give you a graph and say, graph it here? And the reason why it's different is because if you have somebody else's graph paper, you know, it will already have a scale on it of whatever pi whatevers, some fractions of pi down and below. And that means that you're going to have to fit your graph inside their scheme, inside their regulated window. If you don't, if instead you have your own paper and you can make your own scale, then it is a breeze. And here's how. First thing you gotta know, well, first of all, and in fact, I'm just going to deal with this in the negative case. All right. Your particular trig function, whatever that you're being asked to graph, will fit into this scheme. Okay? It doesn't always have to have all of the parts in it. Like, you might just have something like that, where you don't have a C and a D. Your A is a 1 in this case, right? But you don't always have to have all of these pieces in there, okay? But this is as ugly as it gets. And that's why I'm introducing it to you. I'm kind of throwing you into the shark pit and giving you the worst possible scenario out there, okay? But the process of doing this is, well, first of all, let me explain what each one of these variables is. This is the amplitude. And I'm going to go into each one of these and what they are. All right, this is the number of cycles that will occur in 2 pi. This is the frequency. Okay? The period is the width of a wave. And to find the period, to find the width of a wave, you take that b, whatever that b is, and you divide 2 pi by it. Okay? We don't normally talk about frequency in math as much as, say, physics does. Physics talks about frequency all the time. And in all of the contexts you could imagine, sound waves, light waves, and, all that. Okay. C is your phase shift. Okay. This is the sliding of the wave left and right. Okay. Just like when you had, say, the square root of x, or you had the, you had the transformations of functions where if you said something like this, if you were graphing x minus 1, okay, that would be the normal everyday variety of square root of x, but it would be shifted 1 unit to the left or to the right. Which way would it go? It goes in the opposite sign you think of it, right? So since it's inside the pair of parentheses, or the grouping symbol, in this case it's the square root, in the uppercase it's a trig function, it's the opposite direction that you normally expect it to go in. Does that make sense? And you've done that 100 times. And then finally, this is the baseline, or the midline. Okay? For everything except tangent and cotangent, this is the average of the function. Okay? It's the middle of the wave. All right, the order that we're going to do these in is this. You do this first, you do that second, you do this third, you do that fourth. Okay, so you kind of like oscillate, pop, 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 left, right, left, right. Right, left, okay? Again, you're kind of like focusing in on your target, which is X, okay, going from the outside in. All right, now all of this is kind of like I'm just throwing things at you, but before we even go into this, there's an important piece that I need to bring to your attention. Notice my parentheses, and notice that the B is outside of the inner parentheses. Very, very often, you won't have a pair of parentheses. You'll have something that looks like this, maybe. And they'll say, graph that. Well, the problem is that it isn't in the form that I just explained to you. So what we have to do is we have to get it into that form, because the phase shift on this is not pi. In fact, the phase shift is pi over 3. It has to be in that form, okay? Because if you don't pull that 3 out, you're going to wind up with a wrong phase shift. So please be aware of that, because it's a great place to make a screw up, okay? It's a very common error. So star that in your mind and on your notes. Okay? All right. Now that that's been said, now that you've kind of prepared your graph, prepared your equations so that you can start graphing it, I'm going to go through the process one time, and then you can follow along with me with your paper and ruler, or you can just watch me and we'll all do it together later. But let's do an example. Now, this is a strong class, so I'm not going to do the baby steps of like, okay, here's just sine. Now here's sine with an amplitude. Now here's sine with a baseline. Now here's, no, forget it. I'm just going to jump and throw it all at you at once, okay? Because I'm evil, and I like to see you all squirm. Yeah, I'm mean. But anyway, here we go. Y equals 2 sine of 3x minus pi plus 1. Okay. Just like I explained, you gotta pull the B. Do that first. Okay. Now, let's start by drawing a pair of axes. Now, almost all of this is either going to be working in either the first quadrant or the fourth quadrant. There's really no need to begin doing this in the third or the second quadrants. It's like almost, and we naturally, begin thinking about the coordinate grid and putting things on the coordinate grid in the first quadrant, anyway. Let's just work there. And actually, if you don't mind, I'm gonna, now that everyone's got that copied, I'm just gonna shrink it because I really want I want as much space as I can fit. All right. All right, so there's my x and my y. And like I mentioned before, this is first, second, third, fourth. All right. So first thing you're going to do, and notice I am not saying tick marks anywhere. I'm not saying, okay, I'm not drawing my axes and then going 1, 2, 3, 4, 5 up and down my axes or any of that stuff right now. I'm just laying it out, and then I'll deal with that last. Okay, so I'm going to make mine there. All right, cool. Oh, wait, here's another thing that might sometimes help you. A compass. Believe it or not, a compass will definitely help you here. The thing that a compass does is that it allows you to reproduce a width. Okay. Here. No. You probably won't be asked to graph a sine wave on an IB exam. I'll tell you that this is probably one of the most useless skills that I'm going to teach you, because you will never do it, ever, ever, ever. If you ever needed to graph a sine wave, guess what? You'll pull out a computer and graph a sine wave. But because in the process of learning it, you understand the different features of a sine graph. Wait. Okay, yeah, just find a different one. All right, now, the reason why I gave you the compass is so that you can use it like a divider. Does anybody know what a divider is? Have you ever seen those Navy movies or submarine movies or something where you see a guy standing over, sometimes like old, you know, like a navigator on a plane sometimes, and like old B-52s. It's a divider is a compass without a pencil. It's just two pins, okay? And what they do is they walk it down. So for example, I don't have my normal setup for my my normal setup for compass and straight edge, but what they'll do is they'll say, okay, on the scale, the compass is, and I have a compass here. It's actually really lousy. So they go to their map and they say, that distance is the width, is the amount of distance we can travel in a day or in an hour or whatever, right? And what they'll do is they will make a mark and then they'll walk it. And they'll say, okay, it looks like we'll get there in 1, 2, 3 hours and 45 minutes, something like that. Okay, so they're not drawing a big circle with this, and obviously without a lead, you can't do that anyway. But the idea is that it gives you a reproducible distance over and over and over again, and that's why you're going to use it on here. So how do I stop this thing? Go away. All right, anyway. So this was my baseline, was 1. I shifted the wave up 1. The wave will propagate, which is a fantastic word, meaning reproduce as one travels, across this line. Now my amplitude is 2, which means I'm going to go up 2 and down 2. All right? So this is the baseline. This was D, right? So we're going to go up 2 and down 2. So if this is the length of 1, you see, you can use the compass to find out where 2 would be. See how that works? And you see that would give me where 2 is, and that would tell me where 3 is, and so on. See how you can make a reproducible step with it? Is anybody having trouble with that? So are you? Okay, works for me. Remember, you're going to want an amplitude of 2.
No.
Okay. So the corridor that my wave will move through will be from there to there. Okay? Between these lines, between blue lines, my wave will oscillate. Okay? So that's the amplitude. So you start with the D, which was the baseline. You go up and down the amplitude. Now we hop over to the phase shift. Now my phase shift here is a pi over 3. Since it's a negative sign inside the parentheses, that means I'm going to shift it to the right. It's the opposite direction that you normally expect it to be in. Now I don't have a scale. And this is kind of the beauty of this whole system, is that it doesn't have a scale, okay? But one thing that we need to be aware of is that if we put our wave starting there, if that's pi over 3, okay, then if we said that this black line was 0, where the wave hits 0 is going to be important to us. So that's why I generally say draw your y-axis lightly, because you might want to move it a little bit in order to make it fly nicely. Okay. All right, so this is pi over 3. Because I said so. Because I don't have a scale to begin with, so I'm going to make my own. Okay. Why not? Who's to say where it's supposed to be? It doesn't matter. So this is the edge of my box. That's where one wavelet begins. Okay? All right. So now we got to figure out where the wavelet ends, because the whole concept here is to build a rectangle that the wave will live in. So we've got the top, the bottom, and the right hand and the left-hand wall. So we got to go to the right-hand wall and find out where that is. So we go to that formula that I showed you. The period is equal to 2 pi all over the b term. And in this case, my b term is 3. So my wavelet, the width of a wavelet, is 2 pi over 3. And if I started at pi over 3 and I added 2 pi over 3, where would it end? Pi over 3 plus 2 pi over 3, which is pi. That's where the wave ends. Hold on. So this That width is 2 pi over 3. And it started at pi over 3. So I add pi over 3 to 2 pi over 3, and it equals pi. 2 pi over the b term, whatever your b term was. Does this make sense? Okay. All right. So this rectangle is the living environment for a single wave. Okay? All right. Now, we have to take this box and break it up into 4 pieces. Okay? That's done both mathematically and geometrically. Okay? So, what we have to do is we have to find the midpoint of this box. And no, I'm not going to ask you to do compass and straight edge constructions to find out the midpoint of a line segment. In fact, we have a much easier way of doing it. Don't draw that line, but lay your ruler diagonally across it. Because that is the midpoint. Yeah, don't draw that black long diagonal. Just lay your ruler across it. And where the black line, my black line, your ruler, crossed your midline, that point is the center of the box. You see what I mean? It's the dead center of the rectangle. Which means that is the middle of the box, the midline of the box.
Okay, that would be what. Got it.
Oh, wait.
Yeah.
Okay, cool. So you're not really drawing any of this stuff. You're just making the markings so that you can identify it, okay? So this point right here that I just drew, okay, make red, okay? That point is the middle of my wave. So we found it geometrically. We know where it is on your paper. Now we have to say, okay, well, what is it on my scale? So what is a mathematical way of finding the middle number between two numbers? You average them, exactly. So if I average pi over 3 and pi, what is that? Four pi over 6, which reduces to 2 pi over 3. Okay. Yeah. How did I draw the vertical line? Once you put the dot on it? Yeah, I put the dot on the, sorry, man, sorry. Yeah, okay, that's where it's supposed to be. So put a pencil, may I see a pencil, please? So if I put a mark there, okay, where it crossed the axis, I don't have my glasses on, so you gotta bear with me here. Yeah, but hold on, where, I can't really see where. Yeah, you're a little bit off, but that's okay. If you need to fix it, you know, there you go. So yeah, where the diagonal crossed the midline is the middle. Okay. Yeah. Yes. Because, ladies and gentlemen, here's an important little thing that's kind of cool. I wanted it filled. the reason why this works is because there's a property of a rectangle that says when I take the diagonals, the diagonals bisect each other. That's a property of a rectangle. Okay. In fact, it's a property of parallelograms, which a rectangle is. So this, which we don't have to draw, but you can if you want. I mean, if you think your picture is off kilter, you can use this concept to get your picture back in place. Okay. So anyway, what we're going to do now is we're going to use the same thing again to find the other 2 points. Because I said I had to break this box up into 4 parts, 4 regions. So I really need a midpoint, and now I need the midpoint of the midpoint, and the other midpoint of the other midpoint. So here, this is what I mean. I want to find the middle of that red box. So I can use the same idea. To find the next midpoint. You see how I made that? You see how I made that? Okay, good. And you're going to do the same thing for this red. Whoop, wrong one. For the other side. Ah. So, in effect, we have broken this up into what a statistician would call quartiles. And if you remember from your statistics, the quartiles, when you broke up a data set, a whole bunch of numbers, and you wanted to find them 4 quartiles, you take the median, and then you take the median between that point and the other end point, and the end point and the midpoint. So basically what we've just done it geometrically. Now, we're going to find the average of those points to find those values. So find me the average here. What is it? Everyone? Anyone? All of us? None of us? Pi over 2. And that one. Okay. Okay. Now, we've dealt with the A, the B, the C, and the D. We started with a baseline, we built an amplitude, then we moved to a phase shift, and then we did the period. This is where one wave lives. Now, I have not addressed whether I'm dealing with a sine, a cosine, a secant, a cosecant, a tangent. I haven't dealt with any of that. Doesn't matter at this point. Okay? It's totally irrelevant. Every single trig function, whatever it may be, starts with this process. Okay? Only now do we care what particular wave feature, what the curve is. Okay? How do we feel about all this so far? Once you've done it a handful of times, it's quick. You just go pop, 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 done. I am recording this. It's, you know what? Once you've done it a few times, it's really not that bad. I mean, you get cozy with it. It does get better. Okay? Okay. Okay, I'll be nice. We won't do those today. Okay, we will just deal because we won't have time. But doing sine and cosine, you have to just kind of remember what is the sine of 0 and the cosine of 0. And what is the sine of 0? 0. And the cosine of 0? Theft. Right. Okay. So sine waves start off that way, and cosine waves start off that way. Okay, so just so that you will remember what they look like. Okay? Okay, come back. Okay. Now, ladies and gentlemen, take a look. I wanted to show you just where these really kind of do come from. I might have shown you this applet before. Did I ever show you the wave generator? Maybe not. This? All right. So what I've got here is a circle, a unit circle, and a point spinning around the unit circle. Okay? And I'm looking at the height of that dot as it goes up and down. Okay? And I've got this green dot that's moving horizontally. Okay? So for every degree that it rotates, it moves 1/360th along down the road. Okay? So these two are intrinsically linked. So if you look at this dashed line that's oscillating up and down and this dotted line that's moving left and right, there's a point where the two of them intersect. Kind of neat, huh? That's where all of this comes from. Now, you might ask the question, why do we care? It's a valid question, okay? And the reason why we care is because the whole purpose of mathematics is to model nature, to be able to say, all right, how does something behave? Well, nature is full of cycles. Everything from your heartbeat to the rising and setting of the sun, to the tides, to cell division. Okay? Everything in nature, in some way, shape, or form, usually works as a cycle. So what we really want to be able to do is we want to be able to find an equation that constantly repeats itself, a cyclical, or the term is periodic fashion, because we want something that doesn't just go through a point. We want to have it go through the same behavior over and over and over again. Okay? Now, to find the cosine, remember the cosine is the x piece of this. Okay? So now, what I've done is I'm using a vertical line, and that vertical line bounces off of that 45-degree line. See? I know it's kind of weird to look at, isn't it? It's like, yeah. By the way, you should look up the origin of the word mesmerizing. It's named after a man. Believe it or not, there was a guy named Mesmer. Yeah. Mesmer was an early hypnotist. Back when early turn of the century, 20th century. Anyway, so now kind of looks the same, doesn't it? Fluffy's purring over there. So they look a lot alike, don't they? You see? But they're not exactly. I mean, it's a shift. It's a little bit of a shift, that's all. You see? It's not like where one is peaking, one is trough. It's slightly off like that. And in fact, it's off by pi over 2. A quarter of a circle. Okay? So if you look for a moment at, let's see if I can get back here. Where's my, oh darn, where's my vertical line? Okay, can't really see it here, but look at the bottom of the trough of the blue line, the blue curve. It's at a, yeah, it's where the other one crosses the midline. And where this red line goes to a trough is where the blue one crosses the midline. Here you have a peak, there you have the 0. You see? Okay. Tangent is goofy. And turn cosine off. Take a look at sine and tangent and how they behave together.
Gross.
They're perpendicular at one point and coincident at another. What? Coincident.
They come together.
Yeah, where two when two lines cross, the point of intersection is called the coincidence. Yes. Okay, we're running low on time, so enough with pretty pictures. I know, it's fun. It is fun. Okay, so sine starts at 0 and cosine starts at 1. Okay? So let's go back here. Now, we've drawn all of our points. We've got our window. We've built our box. Now I'm just having to draw the sine. Sine starts at 0. It goes to the top, comes back down, hits the bottom, comes back up. That's where you draw your 4 points. This is the only part that matters what trig function it was. If I was dealing with cosine, I would just move my points. And now I draw. Backing it up. If I was backing it up, see, I'm a little bit off. And there. I would just use my compass to say the width between pi over 3 and 2 pi over 3 is this much. So that's where my 0 should be. Okay. If I was dealing with a cosine wave, for example. Yeah. Two, 3, 4, 5. You just got to remember that when it hits the top of the wave and the bottom of the wave, it's tangent at those points. Okay? It becomes tangent to the blue dotted lines. Now, by the way, to help you draw a sine wave, because sometimes kids draw sine waves in weird ways. To help you draw a sine wave, when it begins, all right, It's starting off at a slope of 1. Okay, it's going this way. Then it becomes tangent. Then keep your eyes not on this point, but keep your eyes on that point. And go tangent to it. And then come up. What I don't want to see is this. I do not want to see sawtooth waves, okay, or triangular waves or anything like that. Yeah.
What if it's really close? So,
What do you mean?
like if you have like a really
Narrow box? Well, that's the beauty of this method, is that you can make your box as wide as you want, and your scale is just built appropriately.
What do you do if they already give you a scale?
Then basically do the same routine, but you don't have as much freedom to make it as comfortably wide as you'd like. All right? We will practice this again. Ladies and gentlemen, what I would recommend is to go ahead and try to make another one of these. And I'll give you an equation. How many wavelets? Make 2 wavelets. Yeah, make 2 wavelets. Yeah, please turn in your yellow sheet, and I'll just get those back to you next time, okay? All right. I don't even know who's playing. All right, this episode of The Ronco Show has been brought to you by Sine and Cosine waves.